Hi, my name is Rami Masood, and I'm a third year student studying mechanical engineering at GGU. This is my presentation about aerogel. First of all, let's start with some history. 6500 BC marks the earliest recording of concrete used by Nabatea traders in regions of Syria and Jordan. In 3000 BC, it was then used by Egypt and China. The Egyptians used mud mixed with straw to bind dried bricks, and some form of concrete was used to build the Great Wall of China. In 600 BC, it was used in Rome, and their concrete structures still stand tall to this day. It wasn't until 1824 Joseph Aspdin invented Portland cement by burning finely ground chalk and clay until the carbon dioxide was removed. Aspdin named the cement after the high quality building stones quarried in Portland, England. And in the 19th century, concrete was used for industrial buildings. It was firstly used in England and France between 1850 and 1880, and we've been using concrete ever since. But with the technological advancements and evolution, the demand of something new and better was beginning to arise. And today, we've got ourselves something hopefully better than concrete and potentially breaking new grounds. Meet aerogel. In this presentation, we are going to talk about different points revolving around aerogel. First of all, we will introduce what aerogel is. Then, we will talk about the different types of aerogel that exist today. After that, we will tell the process of synthesizing aerogel, and after that we will talk about the wide use of applications of aerogel. Then we will talk about aerogel in home building and isolation challenges and see how aerogel concrete comes into play. Then we will talk about aerosand, and finally we will talk about aero additives and conclude this presentation. Aerogel is a synthetic porous ultralight material derived from a gel in which the liquid component for the gel has been replaced with a gas. The result is a solid with extremely low density and extremely low thermal conductivity, but stands more than 2000 times greater its weight. Aerogel was first created by Samuel Stevens Kistler in 1931 as a result of a bet with Charles Leonard over who could replace the liquid in jellies with gas without causing shrinkage. It is basically made via the sol-gel technology, which we will discuss later in this presentation. There are different types of aerogel which exist today, and they are oxides, polymers, carbon, and cellulose or starch. Metal oxide aerogels are used as catalysts in various chemical reactions or transformations or as a precursors for other materials. Aerogels made with aluminum oxide are known as alumina aerogels. These aerogels are used as catalysts, especially when doped with a metal other than aluminum. Nickel alumina aerogel is the most common combination. Organic polymers can be used to create aerogels. Seed gel is made of agar, and cellulose from plants can be used to create flexible aerogel. Carbon aerogels are composed of particles with sizes in very nanometer range, covalently bonded together. They have very high porosity and surface areas. They are often manufactured as composite paper. Now, we will discuss the process of synthesizing aerogel. Aerogel is made by a process called the sol-gel process, where sol stands for liquid and gel is a wet solid-like material. A solid can become a gel when the solid nanoparticles dispersed in it can join together to form a network of particles that spans the liquid. This requires that the solid nanoparticles in the liquid which are constantly bouncing around in random directions because of temperature, to bump into each other and stick together when they do. As the soil becomes to gel, its viscosity approaches infinity and finally becomes immobile and fill its and it's not so it becomes not able to fill its container, although it might still wobble back and forth. The transition from soil to gel called gelation. After that, it is left to dry until we obtain the final product, the aerogel. As we've said, uh, aerogel consists of mostly air. Thus, it has very low density. There are many more properties of aerogel, which are high porosity, large sound absorption, low sound velocity, low thermal conductivity, variable refractive index, and flexibility. Also, it doesn't react with melting metals up to 950 degrees Celsius. It has a huge internal surface and its surfaces can be functionalized. It has very high fracture strength and it's hard. There is also what's so called the Knudsen effect, and so aerogels may have thermal conductivity smaller than that of the gas they contain, as they're made up of air. This is caused by the Knudsen effect, a reduction of thermal conductivity in gases when the size of the cavity encompassing the gas becomes comparable to the mean free path. Effectively, the cavity restricts the movement of the gas particles, decreasing the thermal conductivity in addition to eliminating convection. The applications of aerogel are many and useful. It is used in thermal isolation like in houses or cars, where if we are for example in the summer and you need to prevent heat from coming inside to maintain a cold reasonable indoor temperature, using aerogel, a very good isolation material, is a very big deal, as it provides the necessary, as it's like it doesn't only provide the necessary isolation, it also saves costs by lowering the electricity and the cooling or heating consumption, so thus lowering the expenses. It is also used in electronic components, foundry technology, architecture, superlight composites, cosmetics, and even pharmacy. It is also used in different fields like space and sports wear. Spacesuits use aerogel to protect astronauts from the very high temperatures in space near the sun and foreign planets. It is also used in sportswear as it's very light and provides a very good isolation. Uh, there are many challenges that come to mind when building a house or isolating a room or some space, some of which are energy savings and the regulation of indoor climate, as we've discussed earlier. You also need a lightweight material which is also very strong. You also want a very high fire protection, as for example, God forbid, your kitchen blows up and you don't want the rest of the house to go down. So you want a natural construction materials, and so you need a material that protects you from fire, and it's a natural construction material. Also, you want to live in your new house for a very long time, and the very long period problems that appear during this time are fungi colonization. You don't want a material that can cause your walls to be colonized by fungi, thus giving a bad smell and color, and more worse, inviting bugs, and different animals to your house, which will make living there very tedious. You want all the features mentioned in one material, which also doesn't cost much. Aerogel has it all, specifically aerogel concrete. With not only the mentioned features earlier, it is also very cheap. Aerogel concrete is a composite which is made from hydrophobic aerogel granulate and an inorganic binder or matrix such as gypsum, plaster, and cement. But all this luxury comes with some challenges, like the extreme density difference to work with and the bonding strength aerogel matrix interface. Not only in building, aerogel is also used in foundry applications like RF aerogel as a binder, which we will discuss later. Um and it's also used as structural panel and an aerogel wrap as shown in the pictures. Now let's move on to aerosand. So organic aerogels used as a binding material for sand cores and molds can lead to so-called aerosands. The bonding bridges consist of a nanostructured open porous aerogel instead of an easy conventional polymer. The aerosand properties feature an easy removal, features an easy core removal, a very low thermal conductivity, smooth surfaces, and no shrinkage. It doesn't release any gas during casting, where if you did casting before, you know that gas release is a very big deal and might ruin the cast if not ventilated properly. It also has a high bending strength, which depends on the inverse square root of the average sand grain size. Moving on. Since many years, aerogels are specially developed for foundry applications. The newest developments are aero additives, nanostructured aerogels in granular form. The addition of 0.5 up to 5% of aero additives to any common sand binder system leads without any further changes to enormous improvements of the cast part quality of the sand cores. The positive effects are caused by enhanced gas permeability of the sand cores and an extremely high absorption potential for casting by aerogels. Smooth surfaces with reduced roughness are pointed out. Aero additives open possibilities of cast part design which will give new impulses. As you see in the picture on the left, there are obvious improvements of the casting quality all because of using the aero additives. Above is the brass and aluminum with aero all because of using aero additives, and below are the brass and aluminum castings of the aerogels, the casting without aerogels. And so you can see the difference between using an aerogel in casting and not using an aerogel. Aero additives utilize a large surface area, a high absorption capability, and non-wetting with metals. And it is not non-wetting with metals. They granulate from silica aerogel, which is acid-ride, RF aerogel, and carbon aerogel. Its particle size fits to grain size, and its volume fraction is less than or equal 5%. As for the binder, whatever is found in the foundry shop is used, like an RF aerogel binder. To conclude, all the information of aerogel point towards a very brilliant future with these materials and technologies, and potentially opening new possibilities to the world that were never available before. The references of my presentation are provided below, and I thank you for watching my presentation. Goodbye.